We have all felt the sensation of pain, whether it was from falling on concrete or breaking a bone. Although pain is unpleasant, it is crucial that we can feel pain because this ability protects us from harm or further damage. If you can't feel pain and you twist your ankle, you will continue to walk on that hurt ankle, aggravating the condition and preventing your foot from healing. Cell signaling is crucial in the pain processing pathway. When the cells in the ankle are damaged from the injury, the cells release acids that bind with cyclooxygenase enzymes, also known as COX-1 and COX-2 enzymes, which are located in the cell membrane. These acids fit into the COX enzymes like a key in a lock. These enzyme reactions produce lipid compounds called prostaglandins, which are converted into other chemicals that raise the body temperature, cause inflammation, and lower the nociceptive threshold. This threshold is the level of stimulus or pain needed for the nerve cells that relay the sense of pain, or nociceptors, to fire. If you hold the tip of your finger against a pushpin, you will feel the metal on your finger but no pain. But if you press the pushpin further into your finger, there is enough stimulus to cross the nociceptive threshold, causing the nociceptors to fire and signal pain. The nociceptor sends chemical signals called neurotransmitters when pain is detected. These signals reach the brain by traveling from neuron to neuron until they reach the spinal cord, through which they travel up into the brain. The brain then interprets these signals, which is when you say, "Ouch, I should stay off my ankle." There are two main categories of painkillers: over-the-counter types like Advil and ibuprofen, and prescription-only opioid drugs like oxycodone and morphine. Advil and ibuprofen contain competitive inhibitors that bind to the active sites of the COX enzymes. The medicine deactivates the enzymes by taking up the space in the active site that the acids are supposed to bind to. Without available enzymes to produce pain signals, the whole pain processing pathway is disrupted. The medicine acts as a wall that stops the nervous system from detecting the pain. Opiates, on the other hand, work at multiple steps in the pain sensory pathway. They bind to the opioid receptors in cells in our brain, spinal cord, and peripheral nervous system. These opioid receptors are originally used to bind with endorphins, which are brain chemicals that make us feel good. Opiates act as competitive enzyme inhibitors, taking up the active site where endorphins usually bind. Opiates are similar to endorphins but are much more potent, blocking the pain signals and preventing our brains from registering the pain. Opioid addiction is currently a rampant problem. It is highly addictive and requires higher and higher doses for the same effect. As a result, opioid overdoses are extremely common. According to the New York Times, 33,000 people died of opioid overdose in 2015. Good news is, researchers have discovered venom from black mambas as a new potential ingredient for painkillers. The neurotoxins in this venom work as a painkiller as powerful as morphine, but without the negative side effects, since mamba venom affects a different physiological pathway. More importantly, mamba venom is not addictive. Although this kind of medicine still requires progress before medical use, it's a hopeful alternative to addictive drugs.